Okay, so we are going to look at forces in motion on an incline. So, a girl is sledding down a slope that is inclined at 30 degrees with respect to the horizontal. A moderate wind is aiding the motion by providing a steady force of 105 newtons that is parallel to the motion of the sled. The combined mass of the girl and the sled is 65 kilograms, and the coefficient of kinetic friction between the runners of the sled and the snow is 0.15. How much time is required for the sled to travel down a 107-meter long slope if starting from rest? All right. So how much time? Well, that's a player of motion. It's a kinematic sort of question. So we're going to start the process with kinematics. So what is our object? Well, that is the girl on the sled. So she's the one we're interested in analyzing the motion of. That means we need to define both our initial and final. How about when she starts accelerating? Because she's going down the slope. And then when she gets to the bottom, and we know that's 175 meters long. That bottom is given in the problem. All right, so one dimension, even though she's on a slope, it's a single line. So we're dealing with a one dimension problem, and we only have one object. So that's convenient. We only have to worry about the motion of one object. Okay, so let's draw our picture. Here is our slope. We're told that that slope is angled at 30 degrees. Here's our sledder on the sled. There she's holding on. And we need to find an origin. Define an origin. I'm going to define it at the location of the sledder when she begins to accelerate. Okay. So what is our initial position, final position, initial velocity, final velocity, acceleration, and time? What are our players of motion? Well, we know when she starts to accelerate, she's at the origin. So we'll call that 0. When she's done, we got her at the bottom, and we're told that it's 175 meters long. Okay, so that's what that's indicating. Her initial velocity, it says she starts from rest, so her initial velocity is going to be 0 meters per second. And we don't know her final velocity. We're not told how fast she's accelerating or how much she's accelerating, and we're not given time. Okay, so there's our list. All right, well, what are we interested in solving for? Well, we want to know how much time. We're interested in time. So we need to use one of our relationships that gives us time and has some of this other information. Well, that is this relationship. So x final is equal to x initial plus v initial t plus 1/2 a t squared. So my x final is 175. X initial is 0. V initial is 0 times t, but that's okay because it's 0. Plus 1/2, oh, I don't know the acceleration. So just sort of simplifying this, if I want to solve for t, I need that acceleration. So I can't get it from my list, but acceleration, as we've learned, is related to forces. So let's do a force analysis and see if we can determine what that acceleration is. Okay, well, our object's the same. It's the girl on the sled. So what are the forces? How do they point? What's our free body diagram? And we're going to develop the free body diagram as we develop the interactions. Okay, so we know that the girl is interacting with gravity. So we have the sled and the earth. We know there's the force of gravity, and we know that points straight down, earth horizontal. Earth vertical. So here's our free body diagram. There's the force of gravity. Remember that's mg, also known as the weight, just to remind us about using those terms. Okay, well, the sled's interacting with the slope, so that's our normal force. We do have the sled interacting with the slope. It does act perpendicular to the contact, so that's kind of in that direction. So we have our normal force pointing up in that direction. All right. right. It does tell us that there's friction in this problem, so we know there's a frictional force. It tells us it's kinetic, but we would have known that because it is moving. So that's between the sled and the slope. And that opposes the motion, so it's in the direction opposite the motion. So if she's going the slope this way, friction is going back along the slope in this direction. And finally, it tells us that there is a steady force of the wind that is parallel to the motion of the sled and aiding the motion. So we have the force of the wind, that's between the wind or the air, and oops, we always put the object on top. The sled and the wind, or the air. And it's aiding the motion, so it's going to be in the same direction as that motion and parallel to the slope, so along the slope itself. All right, I think those are my only forces acting on this object. So the next we want to think about is we're going after acceleration, so we want to make it easy for us so that that acceleration is in the direction that we're looking at the kinematics in. And that means that the acceleration is along the slope. So we need to make our life easy and identify a coordinate system that is also along the slope. So we are going to want to think about rotating the coordinate system so that one of the axes is in line with the acceleration. All right, now we have a new coordinate system, h prime and vertical prime, and we follow that process of identifying our forces in that new coordinate system. So we have three forces. We're going to think about that coordinate system. Force number one is the force of gravity. Now, in that coordinate system, it does have a component along the horizontal. What is that component? Well, in order for us to have gotten to that slope, okay, we rotated the coordinate system by 30 degrees. So this is 30 degrees. Okay, that's our 30-degree angle. So the horizontal component of gravity is this one, and that's opposite. So we have the force of gravity times the sine of 30 degrees. It's opposite the angle of 30 degrees. Okay? All right, so is it positive or negative? Well, this is the positive direction. It will indeed be positive. Vertically, we have the force of gravity times the cosine of 30 degrees, and it's in the downward vertical direction, so that's negative. Okay, so if you need to pause and just sort of verify those angles for you, this is where it gets tricky, feel free to do that. All right, force number two, well, that's along the horizontal at 105. It's in the positive direction, and there's nothing vertical. Force number three, well, it's along the rotated vertical axis, and it is positive. And force number four, well, that's along just the horizontal axis, and nothing vertical, and it's pointing in the negative direction. So just that force of gravity was the tricky one for this problem. All right, so now we're going to apply Newton's second law, which tells us the force is equal to the mass times the acceleration, the sum of the forces in each direction. So the sum of the vertical forces, the sum of the horizontal forces. Our horizontal is in the direction of the acceleration, so we know that relationship carries through. Vertically, our vertical, there is no motion up or down the plane, so the force sums to 0 in the vertical direction. All right, we want acceleration. Acceleration is in the horizontal direction, so let's keep going after the horizontal direction. We have the force of gravity, so we have mg times the sine of 30 plus 105 minus the force of friction. Now, we're not given the force of friction. We do know that the force of friction is mu times n, and mu is given as 0.15. So 0.15 n is equal to the mass times the acceleration horizontally. So let's just simplify that a little bit. We end up with our 65 times 9.8 times the sine of 30 plus 105 minus 0.15 n equals 65 times the acceleration. We're going to need that n. Let's get rid of a lot of these numbers first. 65 times 9.8 times the sine of 30 plus 105. So we have 423.5 minus 0.15 n equals 65 times the acceleration I want. So I need n. Well, this n is referring to the normal force involved in the frictional force. So the frictional force is between the sled and the slope. So the normal force that applies also has to be between the sled and the slope. But in this case, we only have one normal force. But it's always good to keep that in mind. So that's in the vertical direction. Those forces sum to 0, so we have minus mg cosine of 30 plus n equals 0. We know that n is equal to mg cosine of 30, and that is equal to 65 times 9.8 times the cosine of 30, or 551.66 newtons. So we will plug that back in here. We have 423.5. Multiply that by 0.15 minus 82.75 equals 65 times the acceleration. So 423.5 minus 82.75, you get 340.75 equals 65 times the acceleration. So divide that by 65, and we get the acceleration horizontally is equal to 5.24 meters per second squared. All right, now we're going to go in and put that back in here to solve for our time. So we have 175 is equal to 1/2 times 5.24 times time squared. 175 times 2 divided by 5.24, and then we take the square root of that, and our time is equal to 8.17 seconds. All right, so looking at kinematics, recognizing we need that acceleration that's tied to forces, and since our acceleration is not in our normal kind of Cartesian coordinate system, we're going to rotate that axis to make the acceleration along one of the directions so that it's 0 in the other direction and is consistent with the acceleration direction in our kinematics. Good job.